Okay, here are the solutions for all three parts of example 3. I drew out the subring lattices for Z18, Z30, and Z32. And I'd like us to look at those for a minute and then go on. They're going to motivate our next couple of definitions. So when you look at all our three subring lattices, I'm going to circle a few of the ideals right here. Right there. If you're looking at the highest layer, the one right below the whole group or the whole ring, what do you notice? What do you notice about those circled rows? And in contrast, what do you notice about all the other rows? Well, in my green circled principal ideals, they are all generated by primes. So they're all generated by primes. And of course, they are all in the highest layer. And so this is going to motivate our next couple of definitions. We are going to define prime ideals and maximal ideals. So if we have a commutative ring R and A a proper ideal of R, then A is called a prime ideal if A, B in R and A, B in A implies that A is in A or B is in A. And this may sound familiar to the definition of a prime in the integers, and that's exactly where this name is connected, where it comes from, why we're going to call these prime ideals. And then A is called a maximal ideal if whenever B is an ideal of R and A is contained in B and B is contained in R, then either B is equal to A or B is equal to R. So basically, A is called maximal if you can't sneak any other ideal between A and the ring itself. Okay, so it's the one in the highest layer. There's nothing you can sneak in between. So let's look at an example to visualize this a little bit better. Let's consider, oh man, okay, sorry. Let's consider the principal ideal generated by 3 from our example Z30. Well, so is this a principal ideal? Sorry, it's a principal ideal. Is it prime? Is it maximal? So let's look at prime first. So we have, suppose we have A times B in here. Then what can we say? Well, we have A times B is some multiple of 3. So it's equal to 3k for some k in Z. Okay, but if A times B is equal to 3 times k, another way of expressing this is to say that 3 divides A times B. But if 3 divides A times B, then 3 has to divide A, or 3 has to divide B, because 3 is prime. But if 3 divides A, then A is an element in the principal ideal generated by 3. Or if A divides B, then B is an element in there. And that is our definition of a principal ideal. So this allows us to conclude that the principal ideal generated by 3 is a prime ideal. So it is a prime ideal. And in general, in Zn, ideals of the form, the principal ideals generated by primes are prime ideals and they're also maximal ideals. So we have a prime, generating our principal ideal, then all of those are both prime and maximal. And if you have something other than a prime, it's not going to be the principal ideal generated by something that's not a prime is not going to be a prime ideal or a maximal ideal, because, well, definitely not maximal. You can always sneak a prime ideal between it and the ring itself. And it's also not prime because, well, this condition right here, you couldn't follow through with that.